And we'll give several examples of this important area, which is sometimes called the Internet of Things. Clouds are particularly good for sensors, as we've mentioned before, because sensors are small. And so, at least they typically are small. You could call a giant satellite a sensor, I guess, but most sensors are small. And so those sensors can be processed by individual cores on the cloud. And in fact, a given core on the cloud can probably do multiple small sensors. We used to measure numbers like 1,000 sensors being processed by a single core. And then we got, of course, parallelism because we have lots of sensors. So this is a natural cloud application, which you see every day when you use your smartphone. Here's our usual collections, and here we will be doing sensor informatics. First, let's discuss the Internet of Things, which is really what I mean by sensors. So there is an estimate. I point out many times you can get lots of different estimates from different websites on the available. So, but one estimate is 24 billion devices on the internet by 2020. And most of these will be small sensors sending streams of information sporadically into the cloud. As noted, possibly the most obvious sensor is a smartphone, which in fact has multiple small sensors, like the webcam, like the camera it has, or the accelerometer it has, the GPS it has. Those are little sensors, or even just the typing. As you type in, you're effectively a sensor. And these different sensors stream data. These sensors can also just be monitors of around your electrical devices, or monitoring your home or your children and things like that. And these sensor streams are processed into knowledge, and they will help us our lives in a multitude of fashion. And it is relatively clear the cloud is very, very good at controlling sensors. And it does two things. It can control the sensor, and it also gives the sensor, in the case of the smartphone, access to the world's knowledge. So that's why you can do browsing on your smartphone and do email on your smartphone. It's because you're connected via the cloud to the rest of the world. And there are various sort of other terms which effectively imply this. They usually have the word like smart. There's smart homes and grids is a common term. Intelligent river is a project at Clemson. Ubiquitous city is a project particularly in Korea. And we expect this idea of building smartness into everything, whether it be people or vehicles or what have you, will be of growing importance. And all of these are likely to be supported in the cloud. And a particular example, which we'll see with, say, the autonomous car, is robotics, where robots will get their intelligence from the cloud. And some of these will support science, some of these will support people, and all of them have this natural parallelism of a thing. So this is the classic pleasingly parallel application, where the pleasing, this is 24 billion. That's the number of this estimate of the number of devices. Also, these things are naturally distributed, so these 24 billion devices are not all in one place. They're around the world. So we need the internet to actually connect all our smart things to the clouds, and let's connect the clouds together and give our little devices access to other devices and to other forms of information. So here's a sort of slightly more formal discussion. So a sensor is essentially any sink or source of a time series. So smartphones obviously stream data as a function of time. Kindles do, tablets, Kinects, webcams, these are all sensors. Robots and distributed instruments such as environmental measuring devices are sensors. You can Google Docs, Office 365, WebEx, web pages, these are all sensors by that definition. And ubiquitous cities and smart homes are full of sensors. And as I mentioned, sensors being distributed at grids. And in fact, a simple example of a sensor is a web page. It's sort of a broken sensor because it always gives the same answer. So, or has a very, very modest time dependence. And as I mentioned, we use clouds to consolidate and control and collaborate with sensors. And they all have this pleasingly parallel implementation because sensors are small. They don't load their interface in the cloud so much that you need multiple cores. You do need multiple cores when the sensor does a web search, but we've already discussed that. The sensor needs multiple cores when it does a web search, but it doesn't use web search very often. And so it's quite efficient to have lots of cores doing web search, and those are shared in short time intervals for each of the different sensors. Okay, so the Large Hadron Collider is one of these giant sensors I mentioned. It's all in one place, and as soon as it records the data, it is all sprinkled around the world. And so it does actually end up looking like still pretty big sensors, but more than just one. So your 15 petabytes of data from the Large Hadron Collider ends up very quickly spread around the world. Here's an example of sort of just summarizing sensors as a service. We have all our devices. These are the sensors we use in our collaboration with Kansas to measure data. Here are things like Microsoft Kinect, smartphones, Lego robots, webcams. They're all linked to the cloud where they see sensor processing as a service, which could be map-reduced to link multiple sensors together. And we have a little project developing open source sensor software. Here's an example I gave earlier from General Electric. This is from this nice talk at Berkeley in November 2012, where it points out that the amount of Twitter data every day is much less than the amount of data that General Electric gets from their engines. Their engines are full of monitoring or health sensors, which are looking at what goes on in their engines, transmitting that back to the GE cloud, and that allows us to do much safer transportation. So these are exciting type of sensor, which I expect to see growing use as we do more and more digital IT-enabled industrial devices. So this is some more data on this about the value of the data that this gives from 25,000 engines, 3.6 million flight records a month, and this allows you to derive 18 million parameters every month, and it gives you fuel efficiency, it gives you better capacity, it gives you more reliability. Here's an example from the same meeting in Berkeley, where IBM discusses one of the systems they set in to do vehicle monitoring. So this is an important area with lots of applications. Other people do this, where you monitor traffic, you can actually monitor how busy it is at any given point. You monitor the position and health of various vehicles, and you put all that together to produce a better transportation system. It's relatively clear that this will produce significant improvement. I mean, one trivial thing is that if you really monitor all your buses, you can make certain they keep to time, and instead of getting 5 buses in 5 minutes and then no buses for an hour, those buses really are spread out over time. Here's Google Car, and we see this is full of sensors, cameras. Those sensors either make local decisions or they go off to the cloud. And this is an important issue with cloud support of robots. Some robots, if you have to make your decision very quickly, you can't afford to go to the cloud. If you can wait seconds for your decision, then you go off to the cloud. So you need to look carefully at your computations and do those that are needed immediately and locally, and those that can need more data and hopefully can tolerate a somewhat longer delay, they go off to the cloud. Here's other similar example, drones. These are, of course, self-propelled vehicles that go off. They're used for disaster relief. They are used to monitor sports events. They're used to check for problems with agriculture, crop damage, and things like that. Lots of important uses of these unmanned vehicles, unpersoned vehicles, I should say. Here we have scanning, which is, of course, can be used for lots of different things. It can be used for your ticket when you board your aircraft. You now know, of course, you can download your boarding pass to your smartphone. You can look up, you can scan the tag on every thing in a supermarket and immediately find out how healthy it is, what its price is, and there are a lot of related applications with RFID for monitoring the logistics of merchandise. So these are all exciting well-known applications. UPS and FedEx and those companies use this continuously when they're delivering packages. Here's a collection of sensors I've been involved with: the hexacopter, these some Lego things here, GPS. Here's a little small device. Here's the RFID reader and tag, webcam. The laptop running PowerPoint is with WebEx or equivalent is of course a sensor, and the Microsoft Kinect is a very high volume sensor giving a lot of data. Here's an example we did with NASA some time ago, using a cloud to host the results of GPS sensors, and that's where we measured the performance. Because these GPS data sensors only give rather low data rates, you can put thousands of the sensors on a single node. And this produces sensor data which can be analyzed, in this case, to give early indications of earthquakes.